Okay. Welcome to another video on applied electricity. My name is Dr. Usman Hassan. So we are going to continue from where we stopped, right? We are solving the past question of applied electricity, first semester examination on 2022-2023 academic year, right? Academic year. So let's continue from where we stopped. Okay. Once you've watched this video, if you happen to come across this video and you've watched it, please try and share it with your friends. So if you have a friend and your friend is in first semester, it's most likely that your friend has also taken applied electricity during this first semester. So share with your friend. Okay, so let's get started. We are going to continue from question 91. We stopped at 90. That was yesterday. So today I'm going to solve question 91 to 120. 120 is the last question. So let's get started. So starting with question 91. A junction where two or more than two networks meet is known as, okay, that will be what? A node, right? For example, if you have what we have been told, if you have two or more than two networks elements meet. So let's say you have, for example, you have a resistor, right? This is a resistor. That's one element. Then you have another, you connect it to another resistor here, right? That's your second element. And then you have a third element here, right? You can see here we have three elements, right? So if you have two or more, then that becomes a node. So here becomes a node. So the answer for this is what we refer to as what? A node. So the answer for question 91 is A. Okay. Now let's go to question 92. Question 92. Find the current in the resistor R2 when only the 4 volts battery is acting. Okay. So we are given figure 2. This is figure 2. This is our figure 2 here. You can see to use figure 2 to answer question 92 to 95. So from question 92 to 95, we are to answer those questions using figure 2. Now you have to find R2 when only the 4 volts battery is acting. If you look at figure 2, we have two voltages. We have, right? We have V1 6 volts and then V2 4 volts. So you have to find the current which is passing through R2. You can see R2 in the figure here. This is R2. You have to find the current which is passing through this R2 when only the 4 volt is acting. So this is just trying to tell us to use superposition theorem, right? So we are being forced to use superposition theorem in this question. Now, so if only 4 volts is acting, then with superposition theorem, we know that with superposition theorem, what that means is that we take one source at a time. One source is acting at a time. So you can see we have two voltage sources. Now, if 4 volts is acting alone, right, that means that we are going to turn off the other voltage source. And when it comes to turning out a voltage source, right, if you're having a voltage source, let's say, and you want to turn it off, right, what that means that you connect a wire to it, right, a wire. Turning off means that you are trying to make the voltage to now become 0, okay? So to make that voltage 0, you short circuit the voltage. That means you connect it to a wire, and by doing so, the voltage here becomes 0. Now you just left with only your wire, you connect your wire. That's how you turn off a voltage source. Now if you're having a current source, so this is for voltage. Let's say you have a current source. This is a current source. So to turn off a current source, what you do is that this time, meaning to make the current 0, meaning you just open circuit, right? Meaning you just remove your current source. So we have something of this, right? You remove the current source, and by doing so, now you have an open circuit. Once you have an open circuit, then what? With the open, I mean the resistance is at infinity, so you get a current of 0. So with open circuit, we'll be using this technique. So these are the two techniques we'll be using. So let's continue with this idea that we'll be using. So if we are being told to use, meaning only 4 volts is acting, so I'm going to turn off the other voltage source, which is 6 volts. So that means I'll just come here first. Let me sketch the diagram. Then I have to be fast with the sketch. I'm going to spend a lot of time with this question because it involves a lot of calculations. So this is the sketch of the diagram there. This diagram that I'm just sketching. So here is 1 kilo, right? 1 kilo ohms, another 1 kilo. All the resistors, they are actually 1 kilo ohms. Now we have here 4 volts. And we are now being told that only this 4 volts is acting. We have to find the current, meaning which is passing through this one. So I can have my current here. That's what I'm passing. So let me turn off this. So I will come here, remove the 6 volts which was supposed to be here. Now in that place of it, we connect a wire. So we get this circuit. So this is now a circuit diagram. And we're interested in finding this current, which is I2, based on the labeling. This is R2, here is R1, and this one is what? R3. So I'll label here I2. But this is I2 due to what? 4 volts acting alone. So I'm going to indicate 4 volts attached to it, so that I'll know that. Right. Now, to get this current, you can see that if you look well, you realize that these resistors R1 and R2, they are connected end to end, right? And this is a node, right? This is a node. So with this, we can say that R1 and R2, they are what? In parallel. So you can resketch this circuit diagram if this is confusing you. So let me just resketch it very fast. I'm now going to have my voltage source, which is 4 volts. Now I have my resistor 1 kilo ohm. Then I'm going to now bring R1 so that it will be in parallel with what? So we have this R1 here. Then I can bring my R3. So I have my R3. So this is the same circuit diagram, but this one you can now see clearly that these R1 and R3 are connected in parallel. So to find the current which is passing through this is the current that I'm interested in. Okay, so the current will start moving like this, and then it will come the whole way this way. Okay, here, let me even supposed to be going, current direction here was wrong, supposed to be going up here. So the current direction here supposed to be here. Okay, so when you do this one, 2 is going up, so we have I2 due to 4 volts. So this is the diagram. Now with this, we can now find the current I2 due to 4 volts acting alone. So to find this, I can write here, since R1 and R2 are what? In parallel, and the resistance are the same. Their resistances are the same, which is 1 kilo ohm, 1 kilo ohm. So that means that in getting the equivalent resistance, right, we can just say the equivalent resistance here, or you can call it the overall equivalent resistance. This and this are in parallel, meaning, okay, let me just use their value straightforward. So I have 1 kilo ohm is what? 1000 ohms. So we have 1000 ohm here. You can see it's in parallel with another 1000, which is R3. And then this part, which is the parallel connection here. This part here. Once it's done, you see that is the figure here will now be what, or the value here will now be in series with what? Another 1000 ohm, which is the resistance here. So add here plus 1000. So we have this. When you simplify this, right, I have 1000 ohms times. So even this one, the easiest way is once they are the same, the equivalent resistance here is going to be what? 1000 divided by 2, right? So even if you don't want to use this part here will just be, right? Or you can even just, if you want to, you can just write 1000. So we have here to be 1000 times 1000 divided by 1000 plus 1000 plus 1000 here for the other one. 1000. So 1000 times 1000 divided by another 2000, right? 1000 plus 1000 with 2000. So you divide this by 2000. So you can see that you get here to 500. That's why I say you to just take the resistance over 2, then you get the same answer. So here we get 1500 as the equivalent resistance. Once we've done this, so that simply means is that we now have what? This kind of circuit. Yes, now our 4 volt is in, we now have what? Equivalent of what? 1500 ohms. So this current, which we refer to as I2 due to 4 volts, is going to be equals to, you just take the voltage supply. Now you just apply Ohm's law, which is going to be the voltage, which is which is 4 here divided by the equivalent resistance, which is 1500. So when you do this, what do I get? I get here to be 4 divided by 1500. So that will give me 2.67 times 10 to the power minus 3 amps. So which is what? In milli, that will be what? 2.67 milliamps. So when you come here, you can see that the answer for this question, negative 2, is going to be what? B. Okay, so we get B. Now moving to question 3, negative 3. Determine the value of current in R2 resistor when all the sources are acting. So like I keep on saying, this is just trying to make us use superposition theorem. So now if all the sources are acting, we know that in that case, right, the superposition theory says that if you have a multiple source or independent source in a circuit, right, the current that is passing through an element in the circuit is going to be what? The algebraic sum of what? The current due to each of the independent sources acting alone, right? So with this one, if all with question 93, if all the sources are acting, that means the current which is going to be passing through the R2, which is I2, is going to be equals to what? The algebraic sum due to the 4 volts, right? 4 volts acting alone, plus the current due to the what? 6 volts acting alone, right? That's what you do here. Now with this, we already calculated for the first part, right? The current due to 4 volts acting alone from question 82. Now let's get the current when the 6 volts is acting alone, right? So if we were to come here again, we do the same thing, right? So we maintain 6 volts, we short circuit the 4 volts so that is going to be turned off. So I'm now going to have another circuit diagram, but this time I'm maintaining 6. We are now maintaining 6 volts here. And then we have our resistor. Now in the place of the 4 volts, we turn it off, meaning you short circuit it. Then we have a circuit diagram of this. This is 1 ohm, 1 kilo ohms. Here's another 1 kilo ohms, 1 kilo ohms. So we now have this kind of circuit diagram. You can see that if you compare this circuit diagram to the first one that we did, right, they're kind of the same, like they're kind of similar, right? But the difference is now just the 6 volts, right? If you compare this to this one here, the difference is just the 6 volt. So that means that here the equivalent capacitance, they are all 1 kilo ohms, 1 kilo ohm, which is also 1 kilo ohm. Here the equivalent capacitance, when you try to get it, you see that you get the same answer, the same lesson that we got. So here the equivalent capacitance too is going to be equal to 1. Again, these two are what? In parallel, so meaning we get here 1000. It's in parallel with another 1000 ohms. Plus, then they are in series with what? 1000. So we get here to be 500. So I don't have to do this again, 500 ohms. And then again, we now have one resistor being in series with a voltage source. So the current now due to 6 volts acting will just be the source current, right? They mean the source voltage rather, right? The voltage source that we have, which is 6 divided by the equivalent resistance, which is 1500. So we now get 6 divided by 1500. That is going to give me 4 times 10 to the power minus 3, which is what? 4 milliamps. So I've gotten this. Now, but we are not done yet. So we now go back and look at the formula for the algebraic sum of the current. After this, you indicate the direction of the current. So here, the current direction with this one here, if you look here, this current direction is going this way, right? So again, it's going. So you come and indicate the current direction here, right? On figure 1 here. So if we were to indicate, see this current direction is moving this way. Like when this one, if V1 is acting, so here is turned off, this one will turn off. So you have the current going this way. But so this will be what? Our I2 6 volts, right? Now when V2 is active, you see the current is what? It's from up here, right, down, moving up. So this will be what? Our I2 due to 4 volts acting. So you can see they are in opposite direction. So because of that, when it comes to the algebraic sum, we are going to be using the one that is moving down to be what? Positive, and the current that is moving up to be negative, so that we get here to be, right, so that I'll get here to be the current which is passing through I2 is now going to be the algebraic sum. So the current I2 due to 6 volts is going down, so that will be positive. So I'll get here 4 milli, right? Let me just write, okay, milli. They are all in milli. So minus, okay, milliamps. Then minus this one is going up, so that will be negative. So that will be minus 2.67. Right? So when you do this, so you just take 4. This is also a milliamps. Okay. So 4 minus 2.67. That will give me 1.33 milliamps. So the answer for this is going to be B. Okay. That's for question 93. Now moving to question 94. Calculate the voltage drop across R3. Right? You are asked to calculate the voltage drop across R3. So we come to, here's our R3 here. This is our R3. We have to find the voltage drop. So to find this, you can see this one is quite different, right? If I'm to find this kind of question, I'm now having the liberty to use any other method to solve for the voltage across the R3. Right? Why? Because here, based on the procedure, we are not giving any instruction. So I can use any method to get R3. Right? Because I don't want to use superposition theorem. Right? I can use superposition, but it's going to take much time, I think. So let me use a different method. So I will be using Nodal Analysis to solve for question 84. So we have Nodal Analysis. With Nodal Analysis, what we tend to do is that we are going to we are going to indicate the nodes on the circuit diagram. We have one here. We can have node A, then I have node B, right? So once I've indicated the node, I'm going to make node B, right? I'm going to ground node B here. So you ground node B. Then you have node A. Then node A here will be your reference node, right? Now we indicate now the voltages. So the voltage at A, I'm going to label VA, right? And the voltage at B, because it's grounded, meaning that voltage becomes what? 0. So we get this kind of once we've done this, the next step is now to apply Kirchhoff's current law, right? And before we do that, we assign current to each branch in the circuit diagram. You can see we have 3 branches. This is a branch, this is another branch that we have, and then we have another branch here as well. So we have 3. We have 1, 2, 3 branches. So I'm going to assign the first one to be I1, the second to be what? I2, right? This is my I2, and then I have here to be what? I3. Once I've done this, I can now go ahead, right? I can now go ahead and then apply Kirchhoff's current law to node A. So I have apply Kirchhoff current law at node A. Okay, so at node A here, and in terms of the reference voltage, which is VA. So with this, because the way I've indicated, you can see that I'm indicating minus to positive. The current is starting from negative and going to positive, right? So because of that, you have the node here, node A. I1 is entering, I2 is entering, and I3 is leaving. So the equation becomes I3 because what? I1 plus I2. Now I can express the current now in terms of the reference node, which is VA. So when it comes to, let's start with I3, right? If you look at I3 here, right? We look at where it started from. It started from node A, right? Then from there, it moves to what? Node B. So the node where the current started from, we consider that to be the higher voltage or higher potential, and where it arrives to be the lower potential. So to find the potential difference or the voltage difference, we just take the higher voltage minus the lower voltage. So since I3 originated from node A, that is going to be the higher potential, so which is what? VA, right? So I take VA minus, then it starts from there. You can see that it arrives at node B, which is the lower potential, so VA minus VB over what? When you look at now you look at the branch, this branch that we have here, and within this branch you can see we have what? We have only one resistor there, which is 1 kilo ohm, and that is 1000. So I'll just take this divided by 1000 now equals to I1, and I1 mean we go to the first branch. Again, that one to the same thing. You can see the current originated from V1, right? And the voltage there is 6 volts. So that's the high potential minus VA because it arrives at VA here. So minus VA. Then we look at the branch again. First branch, you see that we have only 1 kilo ohms there. So we divide it by 1 kilo ohm, which is 1000. Now plus the second branch. The second branch here, again, you can see that it originates from what? V2, right? The current originates from V2. So I'm going, and V2 here is what? 4. So 4 minus VA, then arrives divided by 1000 as well. This is going to give us, so I'm solving this. You multiply both sides by 1000. This is VB is grounded, so that's 0. So once I've done this, I'm going to get VA 1000. You multiply by 1000, so the 1000 will cancel. So I just have VA equals to 6 minus VA plus 4 minus VA. So we solve for VA, and this is going to give us 3 VA, right? Equals to, here will be 10. So VA here is going to be equals to 10 divided by 3, right? 10 divided by 3, that will be 3.33 volts. And this is the answer. When you look here, the voltage across the R3 here is going to what? 3.33 volts. Why? Because there's no any other voltage inside that branch, right? And just sign the end at what? VB. Okay. Or if you don't want it this way, you can, if this is hard for you to understand, you can find the current, right? You can find the current, right? You can find the current, which is I3 here. Here is I3. And once you've gotten the current, now you take what? The voltage across R3, what? I3 times what? The resistance. And you get back the same answer. Okay, so you can do it that way as well. But when you look at the possible answer, you can see that there is no 3.33 volts. So here there is a mistake here. I think this part here is supposed to be 3 here. Question -4 here is supposed to be 3. So the answer here will be what? There's a mistake. I think this question was given as a bonus because of this mistake. Question -4. Now moving to question -5. The value of the current control voltage V0 is equals to this beta I0, giving beta equals to 0.8 and then I0 equals to 9.5 milliamps. So here you are just to find the, here supposed to be voltage. There's a mistake here too as well. Okay. Mistake there. It's supposed to be voltage here. Supposed to be voltage. Here's supposed to be voltage, okay? So when you are given V beta and then you just replace this. So V0 here is what? Beta I0 and beta is 0.8 and then the I0 is 9.5 times 10 to the minus 3 because that's milli. So you just take 0.8 times 9.5. So that will give me 7.6 milliamps. So you get this one, right? So this will give you 7.5 times 10 to the minus 3, which is 7.5. Sorry, 7.6 rather. Millivolts rather. I don't know why I'm saying milliamps. Volts. So millivolts. So that will be for question -5. Nodal analysis. Question 86. Nodal analysis method of circuit analysis is mainly based on. We just use nodal analysis, which I wrote here. You can see that in the application of nodal analysis, we are actually using Kirchhoff's current law. So the answer here is going to what? Nodal analysis method analysis mainly based on what? Kirchhoff's current law. So the answer here will be A. If there are n nodes in a network, then how many node voltage equations are required to completely analyze the network? Okay, so here, like we saw here under this question, right? For example, this, or even the figure that we are giving here. Let me erase this. We are done with this. So if we have this circuit diagram, you can see that if we are applying Kirchhoff nodal analysis, right, we only use one equation here, right? Despite that there are how many nodes, right? Maybe there are 2 nodes here, right? So 2 nodes we get only one equation. So it shows that when it comes to the number of equations you will get, it's actually what? N minus 1, right? Whereby n is the number of nodes. So if I'm having 2 nodes, the number of equations I can use to completely analyze the circuit is going to be 1, right? So that means it's what? N minus 1. So here the answer here becomes C. Now moving to question 98. A loop which does not contain any other inner loop is known as a mesh, right? A mesh is simply a loop that doesn't contain any other loop within it, meaning that is not containing an inner loop. For example, here with this circuit diagram here, if you look at the first one here, we can have one loop here. We have one loop. You can see this loop here, one here. It doesn't contain any other loop, or it's not having any inner loop inside it. Again, if you do the same thing for the second one, which is going to be loop 2 here, This one too, loop 2 here doesn't contain any other loop. There's no any inner loop inside in loop 2 here. Now we can have a third loop, which is what? Loop 3. So before I do, let me erase this ones, which is loop 3. And loop 3 here, you can take it this way, right? This is our third. But now you can see for the third loop, we have within this third loop another loop inside. The whole of this are tests. You can see loop 1, right? There's another inner loop inside this one, loop 3. So it's not considered to be a mesh or an independent loop. So the answer for this is going to be mesh, right? Which is an independent loop. A linear, question 89, a linear active resistive network which contains one or more voltage or current sources can be replaced by a single voltage and a series resistance. Whose theorem is this? So this is talking about Thevenin's theorem, right? If you are having a linear active resistive network, meaning if you are just having a network, right? You are having a circuit diagram. We are saying that you can actually replace that circuit diagram with just what? With a voltage in series with what? A resistor, right? So that is what we refer to as what? Thevenin's theorem. So the answer here is B, Thevenin's theorem. Question 100. A linear active resistive network which contains one or more voltage or current sources can be replaced by a single current source and a parallel resistance, right? Whose theorem is this? This one is what? Newton's theorem, right? So when it comes to Newton's theorem, you are having a network, a complex network, you can actually replace by Newton's equivalent circuit, which is going to be consisting of what? A voltage source, right, which is a single voltage, in parallel with what? A resistor, right? So this here is going to what? Newton's, which is C. The answer here is Newton's theorem. A super mesh and analysis could be done when there is what? Dash between any two loops. So this one I didn't really talk about super mesh, but this answer, when we talk about it, meaning they tend to have a common current, right? Let's say you have in a branch, when you have a common current, right? Because the current common, then we say what? This is what? A super mesh. So the answer here should be current. Super mesh could be done when there is a common in what? Between any two loops, right? You have a what? A current source, right? In common. Okay, for example, this way, let me just have a quick sketch of this. For example, if I have a circuit diagram of this, let's say I have a current source here, I have a resistor, then maybe I have a voltage source, a resistor here. This so this is a current source, right? This is a current source. Let's say IS. So you can see within this loop here, within this here, there's a common, right? Within this loop, loop 1 and loop 2, we have a common current. And as a result of that, we refer to this as what? A super mesh, right? I mean, you can just take this as one mesh. So that is what B. Now, question 102. A battery of EMF 15 volts supplies a current of 2 amps for 5 minutes. The energy supplied in this is here. We have what? we are given the battery, the voltage, which is 15 volts. Then we are giving current I to be 2 amps, and then time T is 45 minutes. So 5 minutes here, you change that to seconds. So that will be what? 5 times what? 60, right? That will give us 300 seconds. So that is this the question. We are asked to find the one. We are asked to find the energy, right? We know that energy, or we say power, is a what? The work done over what? Time. And work done is a form of energy. So we can say energy over time. So if we were to make energy the subject, we get power times what? Time. And power is also equals to what? The current times what? Voltage, right? So you replace it, you get current times what times time. So you just replace this, we get 5, which is the current, we get the current, which is giving us 2, right? Times the voltage, which is 15, then times the time here, which is 300. So you just multiply all these together. So we get here to, we can even get here 30, right? 30 times 300, that is going to what? 9,000 energy, so joules. And when you come to the answer, you can see they are all expressed in, we have what? We have A 10 joules, B 3 kilojoules, C 150 kilojoules, and then D we have 9 kilojoules. 9,000 joules is the same as 9 kilojoules. So the answer here is D. So moving to question 103. A DC electric motor consumes 36 megajoules when connected to a 250 volt supply. Here is 250. Let me remove this. It's 250 volt supply for 1 hour. Find the power rating of the motors. So here we are just interested in finding power, right? And from this, you see that we are giving the energy, the electric motor, we are giving the what? The energy, right? We are giving the energy. We already even use this formula, and then now we are being asked to find the power, which we already wrote. We say power, energy is going to what? Or power is the rate of doing work, meaning energy over time. So I can just write power, which is energy over time. I don't have to write this formula. The energy here is 36 megajoules, so 36 times 10 to the power 6 over the time, which is 1 hour, right? 1 hour is going to be, you change that to what? Seconds. That will be what? 60, right? For 1 minute is going to, 1 hour is 60 minutes, right? And then 1 minute is 60 seconds. So that will be 60 by 60. So we get here to be 60 times 60. And this will give us what? So we just take 36 times 10 to the power 6 divided by 60 by 60, and that gives us 10,000, right? So I get the power here to be 10,000 watts. Okay, and 10,000 watts is the same as 10 kilowatts, right? So when you look at the possible answer, we have A, which is 10 kilowatts. So the answer here is A. Now, question 104. Kirchhoff voltage law is related to, when you are applying Kirchhoff voltage law, right? Kirchhoff voltage law, you can see that the law relates to what? Okay, so it says that the algebraic sum of voltages in a closed loop, right? Or in a loop is supposed to be what? Is equals to 0, right? So you can see that the law actually relates to one. A, here we have junction current, no. B, battery EMF, right? So battery, because if you have battery EMF, the sum of this thing is supposed to be 0. Okay, so this could be. Then we have C, relates to what? IR drops. So we now have what? Question D to be both B and then C, right? And this kind of makes sense, right? It relates to what? Both battery EMF and then the drops, because they are algebraic sum. So if I'm having a battery, the algebraic sum involves what? The whole, meaning the battery and then the drop. So here, suppose here will be what? D. Now question 105. Maximum power is dissipated by a load when its resistance is dash the equivalent internal resistance of the source. Here, this refers to, is in regard to maximum power theorem, right? Maximum theorem. And what the theory is saying, that if you are having, for example, a battery, which is a voltage source, Vs, then you have Rs, right? Meaning internal resistance of the battery. Then now you connect that to what? A load resistor, right? RL, right? Now, if you want to get the maximum power dissipated by your load resistor, and this load is sometimes it can be a variable load, right? Meaning whereby it has a range, let's say from 100 to 0 to 100 watts. This is 800 ohms, okay? 0 to 100 ohms. So if you have this theory is saying that if you want to get the maximum power, right, mean dissipated by your load resistor, what that means that you just make sure that you set the load resistance to be the same as the internal resistance of the battery, right? So when you do this, you get the maximum power. So if you were to choose any other value for your load other than the internal resistance of your battery, that means you get this, you don't get the maximum power. So here the answer becomes the load resistance to be equal to what? The internal resistance, right? Its resistance is equal to the equivalent internal resistance of the source. So here is B. Now moving to question 106, right? Use circuit in figure 3 to answer question 106 to 109. So let's start with question 6. Find the current through branch CD. We have C here, then we have our D here, in the circuit of figure 3. So we have to find the current here. Okay, so this is the current that is flowing. That's what we are interested in, this current. Now, with this kind of question, here you can use several methods, right? Because you can decide to use nodal analysis, mesh analysis, branch current method. But what you tend to do, you have to choose the most efficient method depending on the circuit diagram which is given. So if you look at this circuit diagram, if you try to use, let's say, network reduction, you can't even use it. So that one is out of the question. Now you try to use nodal analysis. Here, nodal analysis, because you have a node here and another node here, you are going to have two equations. So maybe in terms of that, maybe you want to avoid nodal analysis. But the easiest one, and then even if you look at the question, the preceding question, is to use superposition theorem, right? Because of the subsequent question. Because if you look at question 107, what is the equivalent resistance of the circuit when the 9-volt battery source is acting alone, right? So let's use superposition theorem, right? If you want to know more about superposition theorem, I solve questions under one quiz question under that. So you search for, I think, MA, was it MA? Apply electricity quiz 1 MA. It's on YouTube. You can search for it. It will give you more explanation on superposition. Now, using superposition theorem, we already used it even earlier, right, to solve some questions. So in using superposition theorem, we are going to take each one acting alone, right? We have two voltage sources, right? We have two voltages, 9 volt and 4.5 volt. So let's start with what? The 9 volt. So let's say the 9 volts is acting alone, right? So this one is acting. I'm not going to sketch most of the graphs here. It means that we have to turn off, right? You turn off what? This in here, the 4.5 volts. So let me just use this to erase it. So it's not there, and here is now we connect a wire, right? That's what you turn this off. Once we've done that, you can see now we have what? A circuit diagram, right? That is what looking like this without this one is turned off. Once I've done this, the next step is now to find the current which is passing through the 3 ohms due to only 9 volts now acting alone. So to find this, now you can see now I'm just having one voltage source and then being connected with what? Resistors. So I just have to look at this circuit diagram. You can see with this circuit diagram now, we have 3 ohms and then another 3 ohms. They are what? In parallel. So the equivalent capacitance for this is going to be equals to 3 ohms here. It's in parallel with what? This 3 ohms. Now, once we've gotten this, you realize that this part now is what? In series with what? 1.5. So I add plus 1.5 ohms, which this wire here. And then this part is now going to be, when you look at the connections, once you connect this, you're going to what? In parallel with what? 3 ohms here. So I put all this into brackets, then I have parallel with 3 ohms. Then after that, I've done for this one now. So now the whole of this part, which I've just finished doing, you can see it's going to be in series with what? 3. So plus 3 here ohms. Now I can just calculate this and I'll get the answer for the equivalent resistance, right? So the overall equivalent resistance for this is going to be equal to 3 ohms is a power of another 3 ohms. So you just take, because the resistance are the same, we just take 3 divided by 2, which is what? 1.5 plus 1.5 here, which is in parallel with another 3 plus 3. So 1.5 will give us 3, power of 3 plus another 3. Again, this one is the same, so that 1.5 plus 3. So this becomes equals to 4.5 ohms. So 4.5 ohms is the overall equivalent resistance when you turn off, right? Remember, we turn off this one. When you turn off the 4.5 ohms. Now, I've gotten this. We are now to find what? I, right? So I've reduced my circuit diagram. So now you apply Ohm's law. Ohm's law is now going to be what? Your voltage source, which is 9, divided by the overall resistance, which is 4.5. So this will be 2, right? 2 amps. 9.5 divided by 9 divided by 4.5 will give us 2. So you get 2 amps. So meaning this part here, you come and indicate. This is 2 amps rather. The current here is 2 amps. Now we are interested in the current which is passing through 3 ohms here. So once we've done this, with this, there's what is going to be in parallel with the whole of this part here. And that part we calculated it to be equals to, so meaning before, okay, the 3 is here, it was what? Okay, here, this part, right? That gave us what? 3, right? So 3. The whole of this is 3, which is in parallel with this. So the current here, which is what? And then we have 3 ohms, 3 ohms. And the current is what? The total current, which is 2 amps entering. So the current that will be passing, because they are of now here, the whole of this is 3 ohms now. So you just take what? The current will now just be what? Divided by 2. So the current passing to 3 ohms here is just going to what? 2 divided by 1. Sorry, 2 divided by 2, right? That will be 1 ampere. So this 1 ampere is going to be the current flowing through here. So we have this part. I don't want to sketch this. It will take a lot of time. That's why I'm doing this way. So I have this now here, which is 1 ampere. This one here, again, when you look here, it will come here. There's a node here. And when you look, once this is not there, it's been turned off, you now have 3 ohms, another 3 ohms. And the total current which is entering node C here is what? A is 1 ampere. So because the resistance are just the same and they are in parallel, so the current for that one too, for this part now, 3 ohms here, is going to be what? 1 here divided by 2. That will be 0.5 amps. So I get 0.5 for this. Okay. So that is for the first part, right? When you are maintaining, when you turn off this in 4.5 ohms. Now we are going to now turn off. So this will be the current passing through the 3 ohms due to what? 9 volts that was acting alone. Let me put the 9 volts here that is acting alone. Now we have to find I3 when 4.5 volts is acting alone. So we come back to the same diagram. Okay, this time we turn off what? The 9 volts. So I'm going to have this way. We connect our wire. This is turned off. Now I have 4.5 volts here. So once I've done this, now I'm going to indicate, we are now going to find again the equivalent what? Resistance, right? Equivalent resistance. So to find the equivalent resistance of this, we do the same thing. So we start from the left side. So this 3 and 3 here, you can see they are what? In parallel. 3 ohms and 3 ohms are in parallel. And after that, once you got this, it's going to be in series with 1.5. So plus 1.5 here. Now, because of this, when you look here, this part is going to now be what? In parallel with what? 3. Parallel with 3. Then plus what? Another 3. You can see that it's similar to the other one, this one that we got. right? If you look well, I think it's the same even, right? Yeah, 1.5, and then this one is 3. Yes, everything is the same to the other one we got. So because of that, we just know that in that case, this one too, equivalent resistance here is going to be at 4.5 ohms. So we get the current again, which is now going to be the total current, you can say, for 4.5 acting alone is going to be this current. That's what I'm trying. So it will 4.5 divided by our 4.5, right? 4.5 volts over. So that will give us 1 ampere. Once we've gotten this 1 ampere, then we come, this is our current, main current, which is 1 ampere here. So again, you can see that this is now our junction, right? So this current, when you look here, this part here, the whole of this, the equivalent was what? 3 ohms. So here too, you take the first one will be what? For this is going to be divided by 2. So we get 1 divided by 2, which is 0.5 ampere, right? So you get 0.5 ampere for this. So we get 1, so here will be 0.5. So this plus is 0.5. Okay, so this will be, and then when you look here, okay, we are interested in the current which is passing through. I nearly made a mistake here. Let me do this. We are interested in this resistor, right? So once we've arrived here and we just, so that will just be for the 3 ohms here. So here we don't have to go further. So the current passing here is just going to be 0.5. So this will be the current due to what? 4.5 acting alone. So it gets 0.5. So now the algebraic sum of current which is passing through the 3 ohms will be what? The current due to 9 volts acting alone. That's the current due to what? 3 due to 4.5 volts acting alone. So with this, I'm going to get the current which is passing through the 3 ohms. Now you look in terms of what? The current flow. This becomes very important, the last part of this. So now I can just come here. When 9 volts was acting alone, right? 9 volts is acting alone. You see the current direction. Current will come here. The direction was going this way. And then when 4.5 volts is acting, it's also current, it's also coming. So they are both in the same direction. So because of that, the algebraic sum will just be the addition. So we got what? 0.5, right? For the 9 volts acting alone, then we got 0.5. Yeah, got 0.5, which was here, right? This is the answer. And then the other one was also 0.5. So we get here to be plus 0.5. That is going to give us 1 ampere. So the answer here is going to be what? A. Okay, so we get here the answer to be A. Now moving forward, 107. What is the equivalent resistance of the circuit when the 9 volts source is acting alone? This one we calculated it, right? when the 9 volts was acting alone, what did we got? We got 4.5. So here is just be 4.5. Okay. Now moving to question 108. Determine the power absorbed by the 1.5 ohms resistor in the circuit. So we look for 1.5 here. This is our 1.5, right? So to find the power dissipated by this, it means that we have to get the one for this 1.5 that I have here. We have to find the current. We know the current which is passing through. This is question 108. 108. So to find the power which is dissipated by 1.5 coulombs, so we get here to be the current, the power will be equals to, meaning 1.5 ohms here, meaning the current, we get the current which is passing through 1.5 square times the what? The resistance. So to get the current which is passing through 1.5, if you look well, the first instant we calculated, right? We got 2, right? And with that 2, we said because this here is 3 and then the equivalent capacitance for this part was 3. So we got 1.5, right? So that will be for the 9 volts. So the 9 volts, the power, the current is going to be for this 1.5 ohms rather, due to what? 9 volts acting is going to be equals to 1 ampere, right? Now you see that this current is going this way, right? Then when 4.5 volts is acting alone, right? Remember we got the total current was 1. For 4.5 acting alone, we got it here, right? Which was 1 ampere, right? 1 ampere. Again, so once we've gotten that 1 ampere, right? The whole of this part was also 3. Again, so you get the what? The current which is going to pass in the 1.5 ohms here due to the 4.5 volts acting alone is going to be equal to what? 0.5, right? Because the other one. Okay. So these are letters. The only difference is now that we are going to see is that now that I've gotten this, and you look at the direction of the current, right? So when 9 volts acting alone, the current is passing through at 1.5, right? Now, when you have 4.5 acting alone, and you look at the current which is going to be moving what? This direction. You can see the currents are in opposite direction. So we are going to take the one moving from what? Left to right to be positive, and the one moving from right to left to be what? Negative. So I'm just going to write the current passing through the 1.5 ohms resistor is going to be 1 minus 0.5, okay, which is 0.5 ampere. So now the power, which is 1.5 dissipated by the 1.5 ohms resistor, is going to be 0.5 square times what? Its resistance, which is 1.5. So we get here to be 0.5 square times what? 1.5. And that gives me what? D, right? That will give me the answer here is going to be 0.375 watts. So you change this to milli, that will be 1, 2, 3. So that will be 375 milliwatts. So the answer for this is what? D. Okay. So we get 375 milliwatts. Now moving to question 109. Okay, 109. Find the current through the 2 ohms resistor in the circuit of figure 4 above. So here we are to find the what? The current which is passing through 2 ohms. So here we have 2 ohms resistor. Now to find this current, right? Again, we are going to be making use of superposition theorem, right? Superposition theorem with this. So to find this current, we are going to apply superposition theorem. The current that is passing through this 2 ohms. So you can see now we have 2 sources, right? But they are current sources. Now when it comes to turning off a current source, we make it open circuit. So we are going to find the current which is going to pass through 2 ohms is going to be equals to the current due to what? Each of these current sources acting alone, right? The algebraic sum of the current due to what? Each of these current acting alone. So it will be what? The current that is passing through 2 ohms due to what? 24 amps acting alone plus the current which is due to 6 amps acting alone. So we have this formula. Now let's try to get first the current that is passing through the 2 ohms resistor due to 4 amps acting alone, right? So we are interested in that current. And to do this, I'm going to now sketch the diagram. When it comes to what? A current source. So we are maintaining first, this is 24. Okay. When it comes to this, the 24 amps is acting alone. So that means I'm maintaining that here. So we have here resistor here, another one here, another resistor. Now the place of what? The 6 amps here, we are going to make it open. Remember I said if you are turning off a current source, you make it open circuit. So we'll make it open like this. Once we've done that, you see here is 6 ohms, right? And here is 4 ohms. You can see here is open. So meaning once this place is open, no current can pass through here, right? So all the current will just pass through this part. It will go through the 2 ohms here and then go through the 6 ohms. So that means that you can even erase this one so that to make it clear for you to see. So you can eliminate this part. So you can now see very well that the current, right? We now have something of this nature. I have my current source here, and that current source is 24 amps, right? So I'll now find the current which is passing through this 2 ohms resistor. And I can just use what? Current division rule. So with current division rule, we can just say the current passing through 2 ohms due to 24 acting alone is going to be equal to 1. Okay, but before we do that, you can see that now 2 ohms and 6 ohms are what? In series, right? So because of that, meaning we have to get the equivalent resistance there. So I can have this sketch another diagram. This one is 4 ohms, but here because this part here they are in series, right? So 2 plus 6, that is going to give me 8. So now I have my current source here. This is my current source, which is 24 amps. So meaning this at this node, the current which is entering here is giving here just 24 amps. So to find the current which is passing through this, so this is 8 ohms resistor, which is going to be the same current that will be passing through the 2 ohms resistor, right? This current here. So this current now, I just use current division rule. So we are going to get the current here to be, we take the other resistor, right, which is 4, over the sum of the resistors in parallel, meaning 4 and 8 are in parallel, so the sum will be 4 plus 8 times what? The current source, or the total current, which is 24 here. So with this we get the current passing through 2 ohms resistor due to the 24 amps current is going to be equals to, here I'm having what, 4, right? So 4 divided by 4 plus 8. So 4 plus 8 will give us 12, right? So here is 12. This part is 12. And then here we get 2, right? So that will give us 8 amps. So I get here to be 8 amps. So this is for what? The 24 amps acting alone. Now let's get the current when 6 amps is acting alone, right? So now I'm having my 6 amps acting alone. So that means a part of what? The 24 amps, I'm going to turn that part off. So that one too, we have this circuit diagram. Here is 4 ohms. We have our 2 ohms here. And we have this 6 ohms. And I have my 6 amps. Okay, let me 6 amps here. Then we now have what? Our 24 amps, but this time I'm going to turn it off, right? So I'm removing, we turn, meaning you make it open circuit. So we now make here to be open circuit. We just remove this. So we get this kind of diagram. So again, when there's current here, this is the junction, right? The current, which is the total current here, 6 amps, is going to get divided. And then when the current here, it cannot pass here because here is open. So the current will just pass through the 4 ohms. So as a result, we can say that we can even erase this, right? Can erase this part. We can now see clearly that the same current will pass through 2 ohms and what? And 4 ohms. So we get the equivalent resistance there. So we can now have this one to be 6, right? 2 plus 4 will give us 6. And then this will now be in parallel with what? Another 6 ohms here. Then here is my 6 amps. So once I've done this, you can see now that the current here is going to get divided, which is 6 amps. I'm interested in the current that's passing through this 6 ohms, which is going to be the same current passing here. But since 6 ohms and 6 ohms, I can just even get this one straightforward, right? Meaning the current passing through ohms due to 6 amps is just going to be 6. So meaning it's just going to 6 divided by 2. Now we get here with 3 amps. Okay, 3 amps. So you can see that with this, once I've done this, now you come back and indicate the direction, right? And then you do the algebraic sum. So I've done this. So the current due to 24 amps acting alone, you see that it's going this direction. And when it's 6 amps acting alone, the current direction is also moving in the opposite direction. So due to that, I'm just going to take the current which is going to pass through the 2 ohms will be equals to. So the part of what? The 24 amps, which is moving from left to right, I'm going to take that part to be positive, then the other one will become negative. So that one we got how much? 8, right? So that will be 8 amps. Then this one is 3 amps. So you get here to be 5 amps. So the answer for question 109 is going to be what? 5 amps here. Now question 110. Calculate the equivalent resistance of the circuit in figure 4 when the 6 amps source is acting alone. So we already even did this, just this one here. We have to find the equivalent resistance, which is this one. Okay, we haven't done the equivalent, but we can just calculate. So this is just the diagram. So you have to find the equivalent resistance when 6 amps is what? Acting alone. So we just have 6 ohms is in series with another 6 ohms. So the equivalent resistance there is just going to be equal to what? Again, you take their in parallel, so their product, meaning 6 by 6 divided by 6, their sum 6 plus 6. So that will be 36, right? Divided by 12, which is going to be equals to 3, right? So we get 3 ohms. That will give us 3 ohms. So the answer for 110 is what? A. Now moving to question 111. A certain generator has an open circuit voltage of 2 volts and an internal resistance of 4 ohms. Determine the load resistance required for maximum power transfer. I explained this one earlier, right? It's similar to the other one. We know that if you are dealing with maximum power, to get the maximum, you make sure that your load resistance becomes the same as the internal resistance. So you can see here the internal resistance is 40 ohms. So meaning if we are trying to find the maximum power, I'm just going to make sure that the load resistance also becomes 40. So the answer here is 40 what? Ohms, right? Meaning the load resistance RL should be equals what? RS, right? This formula. RL should be equals what? RS. And RS is just giving us 40, so this one becomes 40 ohms as well. Moving to question 112. For the given circuit in figure 5 above, determine the voltage drop across the 20 ohms resistor. So this question here has to do with what? Short circuit. If you understand short circuit, this becomes easy for you. Why? Because we know that if you connect a wire, you have resistors in parallel, and then you connect a wire in parallel with those resistors. Because the wire, it has a lower resistance compared to the other resistors, then all the current are going to pass through that wire, right? So that means the other resistors is like the current flow there is 0, right? It's almost 0. So it's the same concept here. When you look at figure 5, right? Figure 5 here, this figure 5 here. So we are having to, for the given circuit above, determine the voltage drops across the 20 ohms resistor. So when you look here is 20 ohms resistor, we have to find the voltage drop. So you see here is a wire. This is our wire, and it's having a very low resistance. So if you look at the other part here, resistors, if we were to find the equivalent resistance for this, you realize that the first part here, we have 30 ohms is in series with what? With 10, right? So the equivalent resistance will be 40, right? Now 40 is going to be in parallel with 20, right? So meaning 40, if we were to find the equivalent resistance, that would be 40 times 20, right? Divided by 60, meaning 20 plus. So you get 13.33, right, for this part. The equivalent resistance of 13.33 ohms. And once you are done that, you see that 13.33 ohms is going to be in series with what? 10 ohms. So when you add it to it, that becomes what? 23.33 ohms. Then after that, you are now going to just have this circuit diagram. Meaning I now have 9 volts, have another resistor, then I have my wire here in parallel with what? 26.33 ohms. So but because this is a wire and it's a parallel with this 26, all the currents are going to pass through the wire, right? So no current will pass through this. Because of that, we say the current here is going to be what? 0. Okay? The current which is going to pass through this part here is going to be 0. And all the current will pass through this because the wire is having a lower resistance. So as a result of that, to just the voltage, in that case, because the 20 volts here, 20 ohms here, you can see it's in the other side of the equivalent resistance. So that voltage becomes 0. So the voltage across the 20 ohms becomes 0. So I'm just going to indicate, so meaning you have this way, voltage across this will be current through this 20 volts times what? Its resistance. Because here the current is going to be 0. No current will pass through the other side because of the wire. So it gets 0 volt. So the voltage drop here becomes 0 volt. Now 113. For the given circuit in figure 5, determine the current generated by the 9 volts source. Now the same figure here that we just saw, but now you are asked to find the current, right? Determine the current generated by 9 volts. So the current here, we are interested in the current, but we know that all the current are going to pass through the one. They are all going to pass through the wire, right? So based on this, we know no current is going to pass through the 26.33 ohms here. So we can even erase that. You remove it because the current flow there is 0. So I can even come and remove this part here. Then I'll just have this circuit diagram. So with this, we can see clearly now the current will just pass through the 10, this 10 ohms resistor, then pass through the wire, then this way. That's how the current will do. Just pass through this part. So now finding the current just becomes what? Ohm's law problem. So we now get the current by taking the voltage, right, which is 9, and now we have is passing only this one resistor here. So divide by the resistance, which is 10, so it gets 0.9 amps. And 0.9 amps, so if you express this in milli, right, it's going to be 900 milli, right, milliamps. Okay, 900 milliamps. So you move this, you get 900. So the answer here becomes 900 milliamps, which is C. Now question 114. A certain generator has an open circuit voltage of 12 volt and an internal resistance of 40 ohms. Determine the load resistance required for maximum power. I think this is a repeated question, right? Yes, a repeated question. So this one again, the answer here is going to be 40. Okay, will be 40. The superposition theorem requires as many circuits to be solved as they are. When we are looking at superposition theorem, if you are having two sources, right, that means you require how many circuits? Meaning you require two circuits, right? One for each source acting alone. So you can see that this question here, the superposition theorem requires as many circuits to be solved as what? As the sources that you have there. So if I have 10 sources, I mean I will be requiring what? 10 circuits to solve. So the answer here becomes C. 116. The ease with which a current flow through a conductor is termed as conductance, right? So if current passes through a material easily or a conductor, we say what? It's a good conductor, right? We allow current to pass through easily. So that's what we mean by conductance. So the answer here is what? B. A sine curve always starts at 0. No, this is wrong. If you have a sine curve or a sine wave, it can start from what? It can start other than 0. We even saw that with the general expression. So if I have a sine wave, the instantaneous voltage will be equal to the maximum voltage times the sine omega t. Then we add what? The phase, right? Plus or minus. So the phase angle here indicates the fact that it can start other than 0. So the answer here becomes what? False. In the Fleming's left hand rule, the forefinger always represents. So if you are using the Fleming's left hand rule, the forefinger, right? Or you call it the index finger, right? Or is it the first finger? It's always represent the magnetic field, right? Remember, the thumb indicate the direction of motion. Then your second finger will indicate the direction of current. So this becomes what? C. Okay, let's move to question 119. The attraction capacity of electromagnet would increase if A, core length increases, B, flux density decrease, C, core area increases, and D, flux density increases. Okay, we know that magnetic flux density, right, is equals to magnetic flux over area. The attraction capacity here refers to what? The magnetic flux, because if you have a magnetic field, it's a magnetic flux that is what? That will cause the attraction to take place. So with question 19, so you see that the magnetic flux density is that's proportional to the what? Magnetic flux density. So if you are increasing the magnetic flux density, meaning you are increasing the magnetic flux here as well. So we have here to be D. Okay, now the last question. When the voltage across a capacitor is increased, the stored charge A increase, B decreases, C remain constant, D fluctuates. So we know that if you have a power plate, which is basically a capacitor, the charge is actually proportional to the voltage, right? So if you are increasing the voltage, you are increasing the charge that are going to be accumulated on the plate. So we have here to be A,